we now have this connection, or we think we have this connection between Pascal's triangle and the expansion of the sum of two numbers raised to a power, where if this power is k, then those coefficients we're going to claim come from Pascal's triangle for rho n equals k. So if k was 2, then we could come over here and say, all right, n equals 2, the coefficients of that expansion of x plus y squared should be 1, 2, and 1. Now let's kind of see how this works. So for the first two rows, it's kind of trivial because x plus y to the 0 is 1, and x plus y to the first is just x plus y, so the coefficients are going to be 1. But let's study x plus y squared and see if we can make sense of why this might be. And really, what are those coefficients in Pascal's triangle really saying? So here I have the unexpanded form of this product. X plus y squared is the product of x plus y and x plus y. Now, for a moment, rather than actually doing all this distribution, we're going to have, the types of terms that we're going to have is, first of all, there's going to be a product between x and itself. So our terms are going to involve, and I'm just going to list these. There's going to be some term involving x squared. There's also going to be some term involving x to the first times y to the first. So x to the first, y to the first. And there's also going to be some term or terms involving y times y, which is y squared. Now, if we look at the expansion of x plus y cubed, which now I'm going to go ahead and write this factor out 3 times. And when we look at this, in terms of the terms involving strictly x's, if I were to I can't really call it foiling, but if I were to multiply, because every component in this ordered pair is going to multiply every component in this, I shouldn't say ordered pair, this sum, and is going to multiply every term in this sum, there's going to be a situation where I get x times x times x. And so there's going to be a term for x cubed. One of the terms is going to involve x cubeds. Now, it could also be the case that I get x times y, which would be x squared y. And there's also going to be a situation where I get x times y, which is x to the first y squared. So I'll put a y to the first there as well. And now there's other ways that could happen. I could get y times x, but that's still the same thing as x times y squared. All I'm trying to list out is the distinct types of terms that we're going to have. And then there's also going to be a situation where we take y times y, and so we get y cubed. Now for n equals 3, we see that there are going to be 4 distinct terms available to us. If we do this expansion for x plus y to the 4th, what we're going to see here is a sequence of terms that look very similar. So in terms of the number of x's that I could grab or choose, that's going to be key in just a moment, the maximum number of x products I could have would be x times x times x times x. And that's x to the 4th. So in this case, my n was equal to 4. The biggest power that I'll have on x is going to be x to the 4th. Now I could just grab 3 x's and 1 y, which would give me x cubed times y. I could just grab 2 x's and then 2 y's and multiply those to give me x squared times y squared. I could grab just 1 x here and then multiply that by the 3 y's in the subsequent factors, giving me x to the first, y to the 3rd. Or I could just multiply all the 4 of the y's together, giving me y to the 4th. So that's 1, 2, 3, 4, 5 distinct terms corresponding to n equals 4. Well, hey, look at this. 1, 2, 3, 4, 5 different coefficients. So every time we increase n by 1, it looks like we're always going to have that many plus 1 more term. So if this was 5, we would have 6 distinct terms we could form. Now, I've used this word choose, right? So how many x's can I choose in my product? Well, if I have 4 factors, I could choose at most 4 x's. Or I could choose 3 x's and 1 y, or I could choose 2 x's and 2 y's, or 1 x and 3 y's, or 4 y's, because that's as many as I have, right? The most x's that can get multiplied together in x plus y times x plus y times x plus y times x plus y is going to be 4 of them. So now I have to make the argument that the coefficients of these will be 1, 4, 6, 4, and 1. Well, how do I go about doing that? So one way I could think about this is I can choose if n equals 4, I can choose up to 4 x's or 4 y's. Can't do both because we're going to get a product of only 4 components, so they could all be x's, they could all be y's, or some of them could be x's and some of them could be y's. Well, I want to figure out the number of ways that I can choose x's, right? Because I can get x cubed y by actually picking an x here, an x from here, an x from here, and a y from here, or I could pick a y from here, an x from here, an x from here, and an x from here. Because again, all of the terms are going to multiply every other term in each of the factors. So I'm going to say that I can choose from 4 terms, I can choose 4 x's, or analogously another way of saying that, and I'm going to write it this way, from 4 terms, choose 0 y's. Okay, so from 4 terms, how many ways is there for me to choose 0 y's? Well, there's only one way that can happen, right? That's to choose no y's. So this is analogous to saying from 4 choose 0 y's, and this is going to be 4 factorial over 4 minus 0 factorial, which is 4 factorial over 4 factorial, which is 1. So there's exactly one way to do that. And that's analogous to saying, you know what, my coefficient for this first term right here is going to be a 1 because there's only one way I can collect 4 x's and multiply them all together. So I'm going to label this as the number of ways that that first term is going to appear. Now you probably already noticed that all of our expansions so far have had only one x to the nth term and one y to the nth term. Now I'm going to go along and do this again. I'm going to say from, so this is going to be for the second term, from 4, or this shouldn't be terms, this should be factors. From 4 factors, choose, well, that has one y in it, so choose one y, which by default then means that the other 3 are going to be x's. So that's asking the question, how many ways are there to choose from 4 items exactly one of those places allocated to a y? Well, 4 choose 1 is 4, and so that tells me that there's going to be 4 ways I could get an x cubed y term. Here's one way, x times x times x times y. Then I could have x times y times x, that's a second one. X times y times x times x, that's a third one. And then I could have y times x times x times x, that's a fourth way. You can probably see how the rest of these terms are going to pan out. Here in this case, in case 3, we're asking for from 4 factors, choose 2 y's, and okay, 4 choose 2. That's going to give me 4 factorial over 2 factorial, 4 times 3, so that's going to be 4 factorial over 4 minus 2 factorial times 2 factorial. And I think up here I forgot the 0 factorial term, and that's equal to 1. So this is 4 factorial over 4 factorial. And so this is going to come out to 6. 4 times 3 is 12 divided by 2 will give me 6. Again, you can use a calculator to compute this. So there are 6 different ways that I'm going to get an x squared, y squared term. And I can proceed in this fashion. Here I could say that this coefficient and I'll go ahead and write them in since I think we have a pattern now. This one, from 4 factors, I want to choose 3 y's, and 4 choose 3 is actually the same thing as 4 choose 1, right? Because from 4 things, how many ways could I make sure one of them is a y, versus from 4 things, how can I ensure 3 of them are y's? Well, that means the other one's an x, and so that will give me x to the first y cubed. So this coefficient here comes out to be 4. And then for our final term here, how many ways are there from 4 factors for me to choose 4 y's? Well, there's only one way to do that. I choose all of them to be y's. So in general, if we want to expand polynomials, we don't have to do this large expansion process. We now have enough firepower to state the binomial theorem. Now this may look kind of daunting at first, but it really is just a very general form of what we've described. Let x and y be variables, and let n be a non-negative integer. Then the expansion of x plus y to the nth power is the sum, so that means add up all of the terms starting at 0, j equals 0, all the way up to j equals n. Basically that means n choose 0, n choose 1, all the way up to n choose n. And the way these are written is to say that when j is 0, that means we just have x to the n, y to the 0, which is just 1, and that's why no y appears here. For the second term, well, now we'll have n choose 1, j is 1, x to the n minus 1, and then y to the j, so in this case j is 1, so that really corresponds to what we had up here as this x cubed y to the first term. And then you can see that the powers on x just continue to decrease and the powers on y continue to increase. So for instance, if I wanted to know how to write x plus y to the 5th power, then the way this is going to look is as follows. It will be n, which in this case is 5, choose 0, x to the 5th, y to the 0, which is just the same thing as saying x to the 5th. Well, how many ways are there for me to draw 5 x terms from 5 factors? There's only one way, so this comes down to 1. Plus, now I'm going to descend the power, so x to the 4th, y to the 1st, and there's exactly 5 ways to select one item from 5, so this is 5, plus 5 choose 2 y's, that'll give me x cubed y squared, and 5 choose 2 comes out, well, I think we could probably even figure that out from Pascal's triangle. That's going to be 10, so that's going to be 10 right there, plus 5 combination 3 x squared y cubed, and that's going to be 10 as well, plus 5 combination 4 x to the 3rd y squared, I'm sorry, this should be x to the 1st, x to the 1st y to the 4th, so let's try that again, x to the 1st, so descend the power of x, increase the power of y, and this comes out to 5. Now you notice that 5 combination 1 and 5 combination 4 are the same thing, because it's sort of the same, asking for if I have 5, how many ways are there to choose one y from 5 factors versus how many ways are there for me to choose 4 y's from 5 factors? This is analogous to saying from 5 factors choose 1 x. So 5 choose 1 and 5 choose 4 are the same. And that's part of the symmetry that we notice in Pascal's triangle, is you see that there is a symmetry. You have 1 and 1 on either end, and then as you move your way in from the left or from the right, the two values there are going to be the same. And so just like here and here, and then you start to get repetitions in the middle because you have 4 plus 6 and 6 plus 4. So you start to see this patternized process. Great. So, and then our final term would be plus 5 choose 5, which is the same thing as saying give me 0 x's, all 5 of the terms should be y. Well, that's the same thing as saying give me all 5 x's and 0 y's. This is going to equal 1. And so our expansion would be 1x, x to the 5th, plus 5x to the 4, y to the 1st, plus 10x cubed y squared, plus 10x squared y cubed, plus 5x y to the 4th, plus y to the 5th. And there we go, there's our connection. This is called the binomial theorem. And we have provided kind of this intuitive sense of how this theorem works without giving it a really harsh, rigorous proof. We can see that if we increase the power to 6, then we're asking the same questions, but we're selecting from 6 x's as opposed to from 5 x's.